This is a Lab 2 report, Magnetic Field of Permanent Dipole Magnets, presented by Xinyu Gong. In this report, I'll go through the introduction and fundamental theorem, experimental process, closed group analysis, and the final evaluation of two what-if questions. The purpose of this lab was to measure the relationship of distance dependence of a magnetic field due to a bar magnet, then compare the experimental data and result with a prediction by computational model derived by Biot-Savart's law. The experiment includes both on-axis and off-axis portion. The fundamental theorems I applied in this lab are Biot-Savart law, the concept of magnetic fields and magnetic moment, and the definition of magnetic dipole. The first part of the experiment is to find the magnetic dipole moments of the bar magnet using the magnetometer app, meter sticks, and the spreadsheet. To find the observation points, the first step is to orientate the phone until it detects 0x component of Earth's dipole, then align the bar magnet with it. The second step is to compute the net Earth's magnetic field online and compare it to the one on app to make sure there's no outside interference. The net Earth's magnetic field I computed is 40.6 mu T approximately. And the third step is to move the phone parallel to the meter stick, marking it on tape where the X maximum component is, then move the phone perpendicular to the meter stick, marking on tape where the maximum Y component is. To record the measurements in spreadsheet, I find places where the magnitude of the X component of magnetic field equals to 20 mu T, 70 mu T, 120 mu T, 170 mu T, and 220 mu T. Then I repeat each experiment 3 times and input the sensor position into the given spreadsheet here. To calculate the distance dependence, I assume that the magnitude of the magnetic field due to the bar magnet is proportional to some constant times some power of the distance, where the constant is represented by k. Taking the logarithm of both sides, I get ln bx equals to ln k plus n times ln r. And using the datasets in the last page, I get the relationship equation to be y equals negative 14.851 plus negative 2.925x, where y is ln bx and x is r. So we know ln k here is negative 14.851 and n is approximately negative 3. I then apply the value of k into the original equation and get the value of mu mag equals to 1.775. Part 2 is about to compare the magnetic field off-axis between the real experiment and closed group analysis. In this part, I try to measure the off-axis magnetic field, and as I only get one long tape, I tested the position of Bx equals to 600 mu T instead of 100 mu T listed in the lab instruction. Measure with the app with an approximately perpendicular distance of 19.3 centimeters, I get a net magnetic field of 267.4 mu T, removing the effect of Earth's magnet. And applying the Biot-Savart law and previously calculated mu mag, I get a net magnetic field of 13.87 mu T. For the first what-if question, if you don't compensate for magnetic north, then all the measured magnetic field from the app will be the sum of both the bar magnet and the Earth's poles. So we can simply assume all the tested result of gas components on the magnetometer is all from the bar magnet. The result final equation will still be the same, but we have to remove the effect of the Earth's magnet in each measurement by subtracting them. And the second what-if question, the magnetic field will double as we now have two same fields adding together. Thank you.